Okay, so we are going to look at reactions of aromatic compounds. At the end of last lecture, we identified what were the properties of aromatic compounds, what were the features of aromatic compounds. And we saw that aromatic compounds had a list of features that they had to be cyclic, they had to be planar, they had to have a contiguous pi system, and they had to have a Huckel number 4n plus 2 pi electrons. I will point out before I start looking at reactions that for a compound to be considered aromatic, then all of these conditions must be met, right? So these are the conditions for aromaticity. So in fact, let's back up a little bit here. So these are the conditions for aromaticity. But it turns out that it's possible, for example, when you look at aromaticity, you can actually divide compounds into three classes. There are those that are aromatic, right? In other words, they fulfill these criteria above. There are those that are not aromatic, all right? And then there are those that are anti-aromatic. So when is a compound not aromatic? And it actually begins when the compound does not, excuse me, when the compound does not fulfill these criteria. So for example, if it's not cyclic or planar, or if it does not contain a contiguous pi system, then the compound is not aromatic. Okay? So it must have these, if it does not have all three of these features, then the compound is not aromatic. So for example, if I have this species, this compound is planar, it's got a contiguous pi system, but it's not cyclic, and therefore this compound is not aromatic, right? Or maybe this compound is cyclic. Let's see, and it's, let's get a cyclic, well, okay, that's fine. This compound is cyclic, but it is neither planar nor has a contiguous pi system, so this compound is also not aromatic, right? So in other words, it must contain, if it does not contain one of these three features, then the compound is not aromatic. Now, sometimes a compound contains these three features. It's cyclic, planar, and got a contiguous pi system, but it does not have a Huckel number of pi electrons. In other words, if, for example, you look at the cyclopentadienyl cation, this is cyclic, tick. It's planar, tick. It's got a contiguous pi system, tick, but it actually has 4n electrons. Compounds like these are said to be anti-aromatic. And this is kind of interesting because these compounds have resonance, right? There is resonance stabilization in these compounds. And yet they are as unstable as aromatic compounds are stable. So this entity is very, very difficult to form. So for example, there's a really nice example. If I take this compound, and I put, say, a tosylate group on here, right? It's a CF3 of a triflate group. This thing ionizes in a flash to give rise to the carbocation, because the carbocation is wonderfully resonance stabilized. And you make the triflate ion, which is a fantastic leaving group. But if I take this species and do exactly the same thing, so I put tosylate on here, this will not ionize to give rise to the ion pair. Oh, this is not top, this is triflate, right? It will not ionize to give rise to the ion pair, even though triflate is a fantastic leaving group. In fact, we say the world's best leaving group is nitrogen. If I manage to make this diazonium ion, this will not break up to give rise to the carbocation, even though it's resonance stabilized and nitrogen gas. And the reason is because this cation, these two cations, was the same cation, this thing is anti-aromatic. So in the same way that some compounds bend over backwards to become aromatic, some species in the same way will avoid becoming anti-aromatic. So reactions which normally would occur for species that have resonance stabilization would not occur if the product is anti-aromatic. Another good example of an anti-aromatic compound is this one, right? This is the cyclopropenyl anion. This is cyclic planar contiguous pi system, 4 pi electrons. So when the number of pi electrons you have is 4n, that means you're anti-aromatic, right? And these species are not formed very easily. So for example, this H, right? If I had a species like this, this H is relatively acidic because when you pull it off, you make a resonance stabilized carbanion. This H is a very low Ka value because if I pull the H off, the anion generated would be anti-aromatic and therefore it does not form. Okay, good. Right, so basically then compounds may be either aromatic, non-aromatic, or anti-aromatic. To be considered aromatic or anti-aromatic, you must be cyclic planar contiguous pi system. If you have 4n plus 2 electrons, pi electrons, then you're aromatic. If you have 4n, then you're anti-aromatic. But even to play the game of being aromatic or anti-aromatic, this is your entry. You must have these three things covered. If you do not have those three, you're simply not aromatic. If you don't have those three, you're simply not aromatic. Okay, so this one is going on here. Okay? All right, so let's get back to reactions of aromatic compound. And we can divide these reactions into basically three types. There are reactions which are called electrophilic, aromatic, substitution reaction. There are a series of side chain reactions. And then there is nucleophilic substitution reactions. In the course of this lecture, we're going to cover the first two, and we leave this one for the next lecture. At least that's the plan for now. So let's start with, these are called EAS reactions. Well, the idea is, if you look at benzene, if I treat benzene with bromine in carbon tet, even though I draw these double bonds, there's no reaction. Which seems strange, because if I take cyclohexene and I treat that with bromine and carbon tet, I would get the dibromo compound. If I treat cyclohexadiene with bromine and carbon tet, I would eventually get the tetrabromo compound, right? And I'm going to ignore stereochemistry here for now. I'm just going to get the tetrabromo compound. And yet, when I've got the benzene ring with what looks like 6 pi electrons, I get no chemistry. In fact, for a long while, the definition for aromatic compounds was that they were compounds that are highly unsaturated but refuse to react by addition. Okay, so the reaction occurring here with the monovinyl and the divinyl compounds is simply addition. Here, with what looks like it's trivinyl, you do not get the same reaction. But it was noticed that if instead you treat benzene with bromine in the presence of iron, what you get instead is this compound, right? What you get is bromobenzene. And this is even stranger still, because not only does the reaction require what appears to be a catalyst, but when it does react, when you do force it to react, it reacts by substitution. It replaces one of the H's by a bromine. So in fact, you can refine the definition of aromatic compounds to be compounds that are highly unsaturated, but prefer to react by substitution rather than addition. And of course, this idea underscores the fact that the aromatic nucleus is somehow sacrosanct. There's something stable about the aromatic nucleus, and that it resists giving up aromaticity. It resists undergoing addition, because such addition would remove the aromatic sextet. You would lose the 4n plus 2 pi electrons. So this kind of reaction then is a substitution reaction. We know that the ring is nucleophilic, so the way the bromine is coming on is as an electrophile. So it really is electrophilic substitution, but it's unique to aromatic compounds. It's called electrophilic aromatic substitution reactions. It's also called SEAR, right? Electrophilic substitution aromatic. Like, for example, you have SN, nucleophilic substitution. This is electrophilic substitution, but it's unique to aromatic compounds. So it's either written as EAS or SEAR reactions. Okay, so how does this reaction go? Well, it turns out that we have a hint, because it turns out the iron reacts with bromine in situ to form ferric bromide. And ferric bromide is a well-known Lewis acid. So what happens in this reaction is that the bromine reacts with the ferric bromide, and that generates a complex which looks like that. And then eventually we will break it up to give Br plus and FeBr4 minus. The Br plus is now a very potent electrophile. It's not as weak an electrophile as bromine, right? Bromine is a modestly weak electrophile. It will certainly attack alkenes, right, and alkynes, but it doesn't have enough oomph to rip 2 electrons out of the benzene ring. So if you convert the Br2 into Br+, the Br+, which is cationic, that does have enough, reactivity to pull the electrons out of the ring. And again, you remember, in order to get a reaction, right? In order to get a reaction, if my benzene is a little bit sluggish and my bromine is also a little bit sluggish, I can get chemistry if I make the bromine much more reactive. So I'm going to convert Br2 into Br+. That's a much more reactive electrophile, and together they have enough energy to jump the barrier. And we've played this game a number of times before. So it turns out in general, the way these reactions go between, say, benzene, right, and some, let's call it EX, where E is the electrophile and X is whatever my leaving group is, these reactions occur in the presence of some MXN, where MXN is a Lewis acid. And, for Lewis acids, M can be aluminum, it can be silicon, it can be titanium, it can be zinc, it can be iron. X can be fluorine, chlorine, bromine, or iodine. There's a whole range of different Lewis acid catalysts. And so these react with the aromatic compound to form the corresponding E species. So this is the nature of the reaction, and just to balance it, you get HX as well. So essentially what's happening then is the electrophile substitutes for H, and the H forms the HX compound. This is the essence of the EAS reaction. How does it occur? Well, they all occur in much the same way, and I'm going to write a generic mechanism for the reaction. The generic mechanism goes as follows. The EX reacts with MXN, and you generate EX MXN minus plus, right? They should start to look familiar. That's what we were doing with the bromine. Okay, EX MXN. The X complexes, we make the species, and now what we're going to do next is we're going to break the bond between, I'm going to write them in steps. So, well, you know what, I'm just going to write it here. what happens next is the EX bond cleaves, and we generate E plus and MXN plus 1. No room here. This bond breaks, and we make E plus and MXN plus 1 minus. Right, so we've converted EX, which might be a delta plus, delta minus maybe, into an E plus. So I've made a modest electrophile into a potent electrophile. That electrophile is sufficiently reactive that it has enough gravitas, if you will, to rip 2 electrons out of the benzene ring. And that will generate this species. As I've drawn this here, I'm going to make this species. Let's say EH, and I'll have the double bond, and there'll be a plus charge here. Now, that species is clearly no longer aromatic. I no longer have 6 pi electrons. I'm not anti-aromatic either because I don't have a contiguous pi system, right? There's a sigma bond here, so there's no p orbital. Right? This is sp3 hybridized, so there's no p orbital. So this is simply not aromatic, right? It's simply non-aromatic. But it is resonance stabilized, right? I can draw resonance forms. In fact, I can go ahead and draw resonance forms for it. And you realize that even though we're not aromatic, we actually are resonance stabilized. And I can draw another resonance form, and that will give me this species. So really, if I were to draw the intermediate, it looks like this. So technically, what I would have done is drawn the dotted line to incorporate the regions where the positive charge is sort of delocalized. But because you were starting off with an aromatic compound, these are normally drawn like this, right? It's normally drawn with a full line to indicate that you've broken aromaticity, because normally in an aromatic ring, you'd have a full circle. So what we're basically saying is, well, you've broken, well, that doesn't work, that you've broken the circle, right? You don't have a full circle anymore because you've lost aromaticity. This entity with the positive charge on the ring and the 2 sigma bonds is called either a Wheeland intermediate or it's called an Arrhenium ion, right? It's called a Wheeland intermediate or an Arrhenium ion. And the Arrhenium ion, you know, it's not aromatic, but at least it's resonance stabilized. So you're not climbing a massively high activation energy barrier. What happens next is that your intermediate, right, which I'm going to start off with, you know, I'll take your intermediate as this species. Right, your intermediate is then attacked by your MX. Right, remember we lost in this reaction, we had lost MXN plus 1. So what will happen is your MX, this species simply pulls off a proton, and you lose MXN, HX, and you generate your substituted product. Right? Now, overall, the MXN is lost. Right? The MXN comes into the reaction and comes back out of the reaction. So it's by definition, right, a catalyst because it's not consumed overall. And it certainly makes the reaction more facile in converting E delta plus to E plus. So it sends the reaction along an alternate lower energy route and is not consumed overall. So by definition, it's a catalyst. It's a Lewis acid catalyst, right, because its function is a Lewis acid. So overall then, this reaction involves the formation of a cation, or something equivalent we see later on, the conversion of a modestly weak electrophile into a much more potent electrophile, in the presence of a Lewis acid, that electrophile then has enough, has enough energy, has enough oomph to pull electrons out of the benzene ring. You make the arenium ion, which is then deprotonated in a step called re-aromatization. Right? This is a re-aromatization step where we go from the arenium ion back to the arene, right? And so aromatic compounds are called arenes because, they're aromatic alkenes, which is a stupid name for it, but they're called arenes. So this is re-aromatization. We are regenerating the aromatic nucleus. So there's several different types of EAS reactions. So let's start off with one, halogenation, right? That's what we did first. And so I'm going to go through that, and we've met this before already. This is where, for example, benzene is reacting with bromine in the presence of iron or ferric bromide, because the ferric bromide can be generated in situ. And we make bromobenzene and HBr. That's the overall reaction. And how does that happen? Well, we saw this earlier. The bromine, a weak electrophile, complexes with the ferric bromide, my Lewis acid catalyst, makes a complex which contains the bromonium species that loses ferric, FeBr4 minus and Br plus. The Br plus then rips out 2 electrons from the benzene and it generates the arenium ion. The arenium ion is then attacked by the ferric bromide. Well, it's not ferric bromide, it's a tetrabromo ferrate 3 species. So you do Br, FeBr3, go bang, bang. You generate FeBr3, so it comes back out. You lose HBr, and you make your corresponding product. Right? So you make your bromo compound. So that we've converted your benzene into your bromobenzene. And the mechanism is exactly the same as the generic mechanism we just went through. Right? So all that varies in this reaction, is what is the E, because it's EX, MXN. All that varies is what is E, what is X, and what is M. And by the way, if we're using halogens as X, they don't have to be the same. So it can be fluorine, bromine, bromine, chlorine, iodine, iodine, it does not matter. Okay? So that's bromination. There's also alkylation. And the alkylation reaction is actually one of a pair of reactions called Friedel-Crafts. Friedel-Crafts reaction. The Friedel-Crafts reaction is kind of interesting. The Friedel-Crafts reaction is kind of interesting. It's one of the first reactions named for an American chemist, and really, in many ways, signaled the advent of American organic chemistry, because really, up until then, organic chemistry had been dominated by the Germans, by the Austrians, pretty much by the Europeans. The Friedel-Crafts reaction is one of the first big reactions that involved an American chemist. So the Friedel-Crafts reaction comes in 2 flavors. Weird. There's Friedel-Crafts alkylation, and there's Friedel-Crafts acylation. And we're going to go through both, because both are actually quite useful reactions. In the Friedel-Crafts alkylation, we'll have benzene reacting with some Rx in the presence of MXN, and that gives rise to the alkyl benzene plus HS. This is the alkyl benzene. Now, some alkyl benzenes have pet names. So, for example, methylbenzene is called toluene. Whoa. Methylbenzene is called toluene. Isopropylbenzene is called cumene. right? So some of the alkyl benzenes have specific names. So what's the mechanism for this reaction? What's the mechanism for this reaction? Wait a minute, something funny happened here. Okay, so what's the mechanism for this reaction? Well, it should be very familiar. I'm going to go on the other page, right? So what happens is my Rx complexes with my MXN. We generate Rx, MXN minus plus. We lose MXN plus 1 minus. That's drawn rather carelessly. MXN plus 1 minus. And we generate our carbocation this time. The carbocation then is attacked or attacks the aromatic compound and generates the arenium ion. The arenium ion, of course, is resonance stabilized. All right, so I'll have R and H. Then the MXN plus 1 attacks the species. We re-aromatize. And we have our alkyl benzene. In the process, we lose HX. We regenerate the Lewis acid catalyst, MXN, right? And we make our alkyl benzene. This reaction is kind of interesting because it generates a species we've met 1,000 times already, which is the carbocation. Now, first things first. Obviously, if R can form a stable carbocation, vis-a-vis, if R is secondary, tertiary, allylic, benzylic, then you do in fact make a carbocation. But if R is unstabilized primary, or if R is methyl, you can't make the carbocation. And in those cases, all that happens, let's say for example, you had a methyl, you had MEXMXN, right, minus plus. So you can't make the methyl cation. Not a biggie. You simply do what looks like an SN2 type reaction, and that would give rise to your arenium ion. It'll give rise to your arenium ion, and you lose your MXN plus 1 minus. So the mechanism is pretty much the same, except that you don't actually make a discrete carbocation. So your nucleophile is not attacking a carbocation. It's attacking sort of the equivalent, right? Sort of the equivalent, because this will have a distinct positive charge on it. Right, so that's point one. So point one is you don't always make the carbocation. Of course, once you make the arenium ion, the rest of the mechanism is exactly the same. So point one is you don't always make a discrete carbocation. Point two is, in the cases where you make a discrete carbocation, we know carbocations can rearrange. So for example, if you were taking this species, right, and you wanted to react this with, say, with, say, N-propyl chloride, and I was using, say, aluminum chloride, well, we know that when we carry out this reaction, we're not going to make, so this is going to make a complex that looks like this. We cannot lose chloride and make a primary carbocation, right? That's impossible. So what we'll do instead, and we've seen this before, is we'll do a hydride shift in tandem with the loss of the species, and that will generate the secondary carbocation, an AlCl4 minus. So the carbocation that the aromatic actually sees is secondary, not primary. So what we'll see in this reaction is that when you make the carbocation or its equivalent, the species, if it can rearrange, will rearrange. So that means that there are certain problems that attend the Friedel-Crafts alkylation. There's certain problems that attend the Friedel-Crafts alkylation. One of them is rearrangement, because you are making something which is a carbocation or its kinetic equivalent, and carbocations will rearrange. The other problem here is, and so of course, obviously, this aromatic reacts with the secondary carbocation, and together And together, what you will get is Q mean as your product, right? What you'll get is Q mean as your product. Oh, that looks terrible. Right? What you get from this reaction, oh, seriously? What you'll get is from your reaction is Q mean as the, whoa. Okay, there's something funny about the edge here. So if I carry out this reaction, my product would be Q mean. Okay? So one problem then is the rearrangement. The other problem is over-alkylation, what some people call polyalkylation. And this actually makes a fair amount of sense, right? The idea is, if I take benzene and I treat it with Rx, let's say AlCl3 or zinc chloride, it doesn't really matter, and I make the alkyl benzene. Well, the reason that the alkyl electrophile attacks benzene to begin with is that the benzene ring is electron rich. Well, that's true, but the alkyl benzene is more electron rich than benzene proper. So that when the concentration of the alkyl benzene starts to rise to some value, there's a threshold point at which even at lower concentration in benzene, it begins to outcompete benzene. So it outcompetes benzene for the electrophile. In which case, what you get is going to be the dialkyl benzene. So you have an alkyl group on here and then another one. So what this means is that there's another R group on here. We don't know whether it's ortho, meta, or para, but it's on here. But now you have two alkyl groups dumping electron density into the ring. And at even lower concentrations than its predecessor, it begins to outcompete both the alkyl benzene and the benzene. So what I'm going to start to get now is trialkyl benzene. So another big problem that's associated with the Freeland-Crafts alkylation is over-alkylation or polyalkylation. So the Freeland-Crafts alkylation is a very useful reaction, but it has two major problems, right? Polyalkylation or over-alkylation and the possibility of rearrangement. Nonetheless, it's a very useful way of making alkyl benzenes. Let's look at the Freeland-Crafts acylation reaction. And that reaction involves, again, benzene reacting this time with an acyl, not alkyl, an acyl halide, let's say acyl chloride, in the presence of a Lewis acid catalyst, let's say zinc chloride, it doesn't really matter, MXN, and that's going to generate the corresponding acyl benzene. Right? I'm going to make the acyl benzene. How, pray tell, does this reaction go? Well, for heaven's sake, the mechanism should be familiar. Right? This will react with, say, ZnCl2. Lewis acid catalyst generates your chloronium ion. We lose the electrophile, so we kick out ZnCl3 minus, and we make RC double bond O plus. This is an acylium ion. Now, acylium ions are kind of interesting. See, there's a double bond, there's a pair of electrons on this species, so I can do a resonance form that makes RC triple bond O plus. Okay, so the acylium ion is resonance stabilized. Well, the acylium ion, right, is positively charged. It's a good electrophile. So it can attack benzene, pull two electrons out, and generate the erenium ion intermediate. Right, so I'll have C double bond O, R, and H. Now I lost ZnCl3 minus, so that species comes back, kicks out, picks up the proton, generates the erenium, generates the arene, so I get re-aromatization. and that makes my product. I'm just going to draw the acyl group on this side, just for simplicity. And I'd lose HCl, and I regenerate my catalyst, ZnCl2. So all of these reactions, they follow exactly the same mechanism, right? The haloalkane, or the acyl halide, attacks the loose acid catalyst. We make a carbocation, or some sort of positively charged species, bromonium, acylium carbocation. It attacks the aromatic ring, rips out 2 electrons, makes another sigma bond. The base that was formed with it, the native base, sucks up the proton, we get rearomatization, we get product. If you look at the acylation reaction, and I compare it to its cousin, the Friedel-Crafts alkylation, there are a couple of little differences. So what were the problems in the Friedel-Crafts alkylation reaction? The problems were rearrangement of the carbocation, right? And why do the carbocations rearrange? They rearrange to form a more stable version. So they go from what would have been primary, which doesn't really form, but like in the case of the N-propyl, it was sensing the development of positive charge, and so we did a hydride shift to avoid that. And if I had a secondary that could rearrange to a tertiary, then it would have done that. The idea is to become stable. Well, if the species formed is acylium, the acylium cation is resonance stabilized. You can't do better than resonance stabilized, which means in the Friedel-Crafts acylation, there is no rearrangement of the carbocation. It's already at the bottom of the energy well. This is an acylium cation, which is resonance stabilized. You cannot do better than that. So, for example, if I made this acylium ion, if I had this thing and it reacts with the AlCl3 and gives me the acylium ion, right? This species is resonance stabilized. The alternative is to do a hydride shift and make a secondary carbocation. Why would I do that? That's only secondary, right? That's only secondary. Whereas if I left it here, this is resonance stabilized. That is actually now, right, a much more stable species. So we will not rearrange. You're already at the bottom of the energy well. So rearrangement does not occur with acylation, Friedel-Crafts acylation. What's the other problem that's associated with the Friedel-Crafts alkylation reaction? And it's over-alkylation. Well, why do we get over-alkylation? Because the alkyl groups activate the daughter products and the granddaughter products so that they are more reactive than their predecessors. If I look at the acylation, that's not going to happen because my product is an acyl benzene. And you will remember that acyl groups, right, just like with Diels-Alder, these groups are electron withdrawing groups, right? They bleed electrons out of the ring. So what you get is a species, in fact, which is less reactive than its parent. It will therefore not compete against the parent. So over-acylation does not occur. So neither problem which is associated with the Friedel-Crafts alkylation, neither one of them raise their head with Friedel-Crafts acylation. That actually gives me a very nice out. So remember that problem we had where we took benzene and we were reacting it with N-propyl chloride, and what we ended up with was cumene, right, with some MXN. Suppose I really wanted to make N-propylbenzene. Suppose I wanted to make that compound. Well, clearly, this approach is not going to work, right? That is not going to work. So here's what I'll do instead. I'll take the benzene, and I'll react it instead with propanoyl chloride, MXN. And I'll convert the propanoyl chloride into the corresponding acyl benzene. Well, that's a ketone. I know how to convert ketones into methylenes, right? I know how to do that. I could either use amalgamated zinc and conc HCl, that's the Clemmensen reduction, or I could use hydrazine and base in the presence of ethylene glycol. Right? In other words, I will do the Wolff-Kishner reduction. I wouldn't do the reaction with the dithiol followed by radionickel because that would saturate the aromatic compound, right? If I use the hydrogen gas and radionickel in the second step with the dithiol, it's going to convert the benzene ring into cyclohexane. But I could certainly carry out reactions on the side chain, which will convert the carbonyl into the corresponding methylene. Okay? And so that's important because you can now see a mixture then of aromatic chemistry, chemistry on the ring, as well as chemistry on the side chain, which we're going to spend some more time on in a little bit. There's one other EAS reaction of note, and that is sulfonation. And in sulfonation, what you do is you will treat benzene, and this one is a little bit different, with what's called no, geez, there are actually two. You treat benzene with SO3. I'll tell you what, let's go back one. Let's keep them with cations first. So let's do nitration. And this is a little bit different from the others too. You'll treat benzene with what's called the nitrating mixture, which is conc sulfuric acid, conc nitric acid. This is a very corrosive mixture, and what you'll get from this will be nitrobenzene. Right? This is nitrobenzene. So how does this reaction occur? And if you notice now, there's no H, there's no MX, there's no Lewis acid catalyst. There's also no simple EX, right? So in this regard, it doesn't really resemble the other reactions in terms of how the carbocation, how the electrophile is generated. The way this goes is as follows. So nitric acid has this structure. And what happens is this reacts with sulfuric acid. And the sulfuric acid donates a proton to the nitric acid. And you get this species. And you lose bisulfate. Now, the immediate question to ask is, well, why does that happen? Why does the H not attack this O instead? After all, this O is O minus, and the answer is it does. It attacks both this O, that O, and for that matter this O. It attacks them all. But the only one that leads to product, right, if it attacks this O, it simply goes on and comes back off. Goes on and comes back off. It's only when it attacks this O that you end up with a very reactive species. You've got a really good leaving group, 1-2 bonds away from a source of electron density. Does that sound familiar? Not only that, but you've put 2+ charges on adjacent atoms, which means there's massive repulsion. So the repulsion between these, which wants to kick off the water, in combination with a good leaving group, 1-2 bonds away from a source of electron density, means my reaction goes forward. I will kick out water, and I'll generate the nitronium ion. At this point, the mechanism is exactly the same as all the others. The nitronium ion will attack the benzene ring, rip out 2 electrons, make the rhenium ion. The water molecule that is lost in this step serves as the base, pulling off the proton, doing a re-aromatization, and I make product. So I can make nitrobenzene. And the last of the lot is sulfonation. And in sulfonation, you know what, I feel compelled, I feel compelled to complete this. So I'll have benzene attack the nitronium ion, and that's going to give rise to the rhenium ion, which I can draw like this. So that's NO2H. Where am I going? So there'll be a plus charge here. And then the water that is lost in this step does the re-aromatization. Crikey. So I'm going to lose H3O plus, and I'll make my product, which is nitrobenzene. Okay, just to complete that. sulfonation is also different from the others. In sulfonation, we treat benzene with SO3, sulfur trioxide, so there's no actual cation, dissolved in conc H2SO4. Very often, people write this mixture as H2S2O7. In other words, if you add H2SO4 to SO3, you get H2S2O7. This is called oleum, and it's also a very, very, very corrosive mixture. In fact, it's also called fuming sulfuric acid, because you see droplets of SO3 above the liquid. It's a very nasty mixture. But if you react benzene with oleum, what you get is benzene sulfonic acid, right, as your product. And what's also interesting is this reaction is also an equilibrium. So you get benzene sulfonic acid and as your product. And the reaction is an equilibrium. So how does this reaction occur? The benzene reacts with SO3, and you generate, this is an equilibrium, you generate your rhenium ion, okay, and then your mixture will contain this concentric acid. There is some water in the system that functions as a base, sucks off the proton. That's an equilibrium, and you end up with so you lose H3O plus, and you end up with SO3 minus. Right, so that's a benzene sulfonate anion, and of course with the H plus, it's essentially benzene sulfonic acid. The reaction is reversible, so that if I took the sulfonic acid and I heated it with water, it simply goes backwards. Right, and that actually is very useful. So really, there are two differences in this reaction. One is that the electrophile is not actually a cation, as it is for the nitration reaction, the bromination, the Freelicrafts acylation, the Freelicrafts alkylation. Here, the electrophile is actually neutral. It's SO3. And secondly, all the other reactions went to completion. This one is an equilibrium. Okay. Right. So we know how to put groups then on the benzene ring, with the benzene ring functioning as an electrophile. There are two other things we mentioned, and then I think I'll stop. We pick up from here in the next lecture. Suppose I had an aromatic compound that already had some substituent on it, some group X on the ring. What I want to do now is add another electrophile, Y+. So I'm now puzzled by two things. And the things are, one, where does Y+ go? In other words, do I make the ortho compound? Do I make the meta compound? Do I make the para compound? Or do I make all three? And if I do, what are the relative yields of those three compounds? That's the first issue. And then the second issue is this reaction more or less difficult than if I were trying to do it by adding Y+ to benzene? So my questions are about the directing nature of X. Where does X send the incoming electrophile? Ortho, meta, or para? That's its directing ability. That's a regiochemistry question. And then the other feature of X is, does X activate the compound relative to benzene, or does X deactivate it? Right? That's a question of kinetics. So we are interested in the effect of X, on EAS reactions. And the effect is both directing and activation, deactivation. Right? In other words, is the reaction more facile than with benzene proper, in which case X is an activator, or is the reaction more difficult than with benzene proper, in which case X is a deactivator? Well, the first one is actually, well, we do the second one first. The second one is actually very easy to answer. And this is something we've seen before, starting with the disorder. So what makes the benzene ring a nucleophile? And the answer is, it's got pi electrons. So if I put an electron-releasing group on the ring, the electron-releasing group is an activator. So what are my ERGs? Just to remind us, they can function either by induction or by resonance. Right? So if I'm an ERG, my electron-releasing groups typically are alkyl groups. Or they can be O, or they can be N. Some group with a lone pair of electrons. It typically is a second period element, so it makes good p orbitals with the carbon. Electron withdrawing groups, on the other hand, tend to be halogens or positive by induction. By resonance, they're X double bond Y or X triple bond Y, right? So they're cyano, they're carbonyl, they're sulfonyl, they're nitroso, and so on and so on and so on. So electron-releasing groups are activators. Electron-withdrawing groups are deactivators. I'll give you a good example. If I take benzene, and I treat benzene with, let's put benzene in the middle. If I take benzene, and I treat benzene, we've talked about this before, with bromine in carbon tet, there's no reaction. Bromine is not a sufficiently strong electrophile. But I can certainly get chemistry with benzene and bromine in the presence of iron, in which case I get the monobromo product. I add the catalyst. If I take nitrobenzene and I treat that with iron and bromine in carbon tet, I get very little reaction to give product, right? But the reaction is very, very difficult. I'm going to put this in square brackets because the yields are going to be very, very low, right? Because the nitro group so deactivates the ring, you get very little of this product at all. In fact, the nitro group is so strongly withdrawing that you can use nitrobenzene as a solvent for EAS reactions. It is so strongly electron withdrawing. Okay. If, on the other hand, I take a hydroxy group and I put it on here, so OH or an amino group, so I have aniline or I have phenol. These are such potent activators that the reaction occurs, well, typically using water, the reaction occurs instantaneously. And what you get is a white precipitate, and I'm going to do the one with the phenol, and your product is not just one bromine on here, but three. Right? So you get an immediate white precipitate of the tribromophenol or the tribromoaniline on this reaction. So with benzene, there's no reaction. I have to use a catalyst. Even with a catalyst, nitrobenzene reacts very, very sluggishly. Right? It reacts very sluggishly. And that's because the nitro group is strongly electron withdrawing and therefore deactivates the molecule. You stick a phenol on, the reaction occurs immediately. Right? There's no need for a catalyst. It just occurs with bromine in water. And it doesn't stop at one bromine. It puts on three. And the reaction is as fast as a precipitation when you add silver nitrate to HCl. The reaction is that fast. So the OH group and the NH2 group are so activating, the reaction occurs virtually instantaneously. Okay, so we will stop here and pick up from here on Monday. Or should I do the... Yeah, no, let's just stop here. Pick up from here on Monday. Okay, thank you.